So let us start a new chapter, and which is very important. The name of the chapter is wave motion, right? In this chapter we will discuss the wave, right? Basically wave in the string and the sound wave. Our topic of the discussion will be, right? So let us start with uh, wave motion, right? What is wave motion? To understand the wave motion, let us consider a particle is over there. Suppose this particle has the mass m and it is speed v, right? So when you throw, suppose this is the particle, when you throw this particle, so what will happen? Where it goes, after some time its velocity becomes, suppose the v dash, right, in air or somewhere. So where it go, it carries the energy with itself, right? When you throw this particle, also the mass is transferred from one point to another point, from point A to point B. The mass is transferred, also the speed, and therefore the kinetic energy is transferred, right? Therefore its momentum is transferred. So when a particle is thrown, right, move, particle is thrown, right, from one point to another point, from one point to another point, right, from one point to another point, it carries energy plus momentum with itself. Where it go, right? That is the thing. So it transfer the energy, right? It transfer the energy from one point, to another point, right? And here the actual movement of particle takes place, actual movement of particle, or you can say the actual movement of mass occurs. You understand? The mass itself, this pen is going to other position, right? Now there is another way to transfer the momentum and energy, right? There is another way, right? There is another way by which the energy and momentum, energy plus momentum is transferred from one point to another without actual movement of mass, right, or medium. Is it clear or not? And that way is called the wave, and that is called wave. So what is the wave? Wave is nothing but the way to carries the energy and momentum from one point to another point, but the mass is not transferred. Is it clear or not? For example, if you consider this is the water filled in the pond, right? And suppose there is a paper boat. Right? Because of some reason, if you thrown a stone over here, right, at this point, so what will happen? The surface waves are produced, right? When you throw the stone, the water will be go up, go down, right? When you throw the town, right? And after this, the wave is start. This medium is start oscillating up and down. Therefore the wave is produced. Is it clear or not? The wave is produced. After some time you will see that the wave start moving from left to right, or also they move start from this direction also. After you will see that this boat is also moving, right, up and down. Is it clear or not? If you take the another boat after this, right, boat start moving up and down. After, you will see, right, this boat is also moving after some time up and down, but this boat does not move left and right. Are you getting? This boat does not move left or right. So after, here you provided the energy. All right, energy is provided at this point. After some time, it transferred to this another point. Is it clear or not? The energy is transferred from one point to another point. Also, again, the energy and momentum is transferred to one point to another point, but the boat does not move itself. What does it mean? The transfer of the mass does not takes place. Only the energy and momentum is transferred. Right. That is transfer of energy and momentum takes place. Momentum takes place, not the mass is transferred, not the mass is transferred, or you can say takes place without movement of mass, without movement of mass. So there may be the another example of this type of the wave. For example, if you take a string, right, a mass is hanging over here, suppose, and now this string is moved up and down by your hand. When you move it up and down, or just a pulse is created, you can say. So this pulse start moving right towards right. After some time, if there is a mass m, so you will see the after some time the mass will be moving, right. And when this pulse is, you can say, the string is long, right. After some time this pulse is moving, so also the mass, right, start moving on this pulse. This pulse is passed, the mass will remain as it is. So you will see the mass remain on its position, every particle of the present on the string. This is the medium through which the wave is passing, right. So the particle moves and up and down. This particle move and then comes down. The energy is transferred from one point to another point. Also, energy is transferred to this mass, but the mass does not leave their position, its position. Only up and down takes place, not the left and right. You understand? So this is the another way of transfer the energy from one point to another point. The another example, I'm writing this side. The another example you can write the sound wave. For example, the sound wave, right? And different types of the wave. Whatever the type of the wave, it is the example, or it is the way to transfer the energy and momentum from one point to another point without actual movement of the mass, as we have seen in this example, where the particle carries the mass, energy and momentum with itself, right. Copy this. So the wave is nothing but the way to transfer the energy and the momentum from one point to another point. And the important thing is, when the wave is produced, right, whether it is the wave on string, right, wave in string, and whether it is sound wave, right, sound wave, right, the wave move from one point to another point with some speed, right. You may write wave in string or sound wave. The speed, right, speed of the wave, speed of the wave depends upon depends upon two following property of the medium, two following property of medium, What are those property? First is elasticity. We have discussed the elasticity. And second property is inertia. This is the very important point. right? I will discuss the speed of the wave depends upon the following properties of the medium, right? When the wave in the string is produced, suppose there is a string and you are moving up and down your hand, the wave will move from left to right or right to left. So this speed depends upon what? Say elasticity and inertia. Is it clear or not? Copy this. So we can divide the wave in three categories, right? Or you may write the three types of the wave, three types of waves. What are those? First is the mechanical wave, right? Second is the electromagnetic waves. And the third is what? The third is matter wave, right? Matter waves. The mechanical waves are the waves we are going to discuss, and they the required the medium to propagate. To propagate. You understand? The electromagnetic waves are the wave no medium is required. No medium is required. Right. For example, light wave. Right. Right. Light is a wave. Right. Radio wave. Do you understand? All the electromagnetic wave, like the Wi-Fi communication. The Wi-Fi is coming to your laptop or mobile from the device, right? From the fiber, geo fiber, like that. So and signals are coming in your mobile from the tower, nearby tower. So these signals are coming in the form of the wave, right? Suppose there is a tower, right? There is a tower and there is a mobile and there is an antenna inside the mobile. Also there is an antenna, or you can say the receiver in your laptop or iPad, whatever you are using, right? So signals are coming in the form of the electromagnetic wave, and they do not require medium as in case of mechanical wave. For example, what is the mechanical wave? For example, wave in sound wave, right? We are speaking, right? If the medium is not present, that is the air molecules are not present, our sound cannot move from one point to another point. In vacuum, the sound cannot be propagate. You cannot listen the sound. Is it clear or not? The another thing, the wave in string, right? So without medium, these mechanical waves, sound wave, wave in string, the water surface wave, right? And so many waves are there we are going to discuss. Without medium, they cannot propagate. And the electromagnetic waves is the second type of the wave. No medium is required. For example, light wave, radio wave, right? And the matter wave, right? This is the different parts of the wave, and this wave is associated. This wave is associated with associated. This wave is associated with fastly moving particles. Fastly moving particles. Moving particles like, right, electron, proton, neutron, etc. Right. We will discuss this matter wave in the class 12. Also, the electromagnetic wave will also we will discuss in the class 12. There is a one chapter for this, and for the matter wave in the modern physics we will discuss this. But here now we are going to discuss only the mechanical wave, which require the medium. Without medium they cannot be propagate. And now this mechanical wave, right, mechanical wave can be classified, can be of two types, two types. What are those? First, right, first is the transverse wave, and the second is longitudinal wave, longitudinal wave. So the transverse wave and the longitudinal wave, basically we are going to discuss. The transverse wave is nothing but the wave in the string, like guitar string, right, or a string. If you take, then oscillate up and down, the transverse wave is produced. For example, the sound wave, right, sound wave propagate in the medium, right, in the form of compression, rarefaction. We are going to discuss this, right, copy this. So now we will discuss the two types of the wave. First is transverse wave, right, and here the second is longitudinal wave, right, longitudinal wave. All right, what is the transverse wave? For example, wave in string, wave in string, wave in string. Suppose this is the string, right, when you move your hand up and down, right, so the particle start moving like this, up and down, right, they are moving up like this, they are moving down, right. If you consider the any particle present on the string, it move up and it move down. Is it clear or not? While the wave is moving towards left or right, right. So particle oscillates, particles in this transverse wave, particle oscillate perpendicular to the propagation of the wave, propagation of the wave, right. This is the important thing about their mean position, about their mean position, about their mean position. Is it clear or not? Right. For example, wave in stretch string, wave in stretch string. The second wave, the longitudinal wave. You can consider, for example, the sound wave, right. Sound waves, suppose this is the speaker, right. From this speaker, the sound start propagating in the form of compression. These are the compression I will discuss, and the rarefaction, right, in the form of compression and rarefaction. In this wave, suppose this is the speed of the wave from left to right, right, and if you consider the any particle, the medium particle, so it oscillates about its mean position to and fro along the direction of the propagation, right. Here the particles oscillate in the direction of propagation of wave, propagation in the direction of propagation of wave, right, about their mean position, Is it clear or not? About their mean position. Fine. For example, the sound wave. Listen, if you consider the transverse wave, it moves in the form of crust. These are the highest point. Suppose this is the speed of the V. These points are the crust, right? The maximum amplitude from the mean positions are the called crust, and these the minimum, the lower displacement of the particle. These points are called trough. I think class 9th and 10th you have gone through. I will discuss it further. While the sound wave or the longitudinal wave, particle oscillate about mean position to and fro along the direction of propagation in the form of, right, and sound wave travel in the form of compression, right, and this is the rarefaction, right, rarefaction, compression and rarefaction. Is it clear or not, you tell? Right. Important thing, this transverse wave can be produced only in solid, so this wave can be produced only in solid, not in liquid, and gases. It cannot be produced, the transverse wave cannot be produced in liquid and solid, liquid and gases, since they cannot sustain, liquid and gases, they cannot sustain the shearing strain. Or what does it mean? The shearing strain cannot be produced in the liquid and gases. For example, if you consider the solid, suppose any solid, a wire, so wire can be twisted, wire can be moved and down, but if you consider the liquid, are you getting? You cannot move the liquid up and down, right? By your hand you can take the liquid up and down, but shearing stress or shearing strain cannot be produced in the liquid. What is the shearing stress and the strain? Mean, when you move up the solid, suppose this is the wire, right, suppose this is the wire, when you move up the solid, is it clear or not, like this, so these molecules oppose the motion of this solid, of these molecules, you understand, and the restoring force is produced. For example, if you pull this and the tension is produced, so the intermolecular forces is produced inside the solid. But if you take the liquid, if you try to pull the liquid, it will pull up. No other molecule can produce the shear stress or some other stress. Is it clear? In the same type of thing is in gases. In the gases also, this transverse wave cannot produce, because if there is a gas, you take your hand, so all the gas come with your hand. No opposite force is applied in the gases, right? While the longitudinal wave can be produced in all three types of matter, right, matter. What is that? In solid plus liquid plus gases, right? Why? Because they sustain, since they can sustain compressive strain. Compressive strain mean, to produce the longitudinal wave, right? To produce the longitudinal wave, you have to push or pull the medium along the direction of the propagation. So in the solid it is possible, in the gas it is possible also. The compressive strain or stress is also possible in the gases. So this is the transverse wave, propagate in the form of trough and crust, right? Molecule oscillates, or the medium particles oscillate up and down, right? Or you can say the perpendicular to the direction of propagation of the wave. In this case, the medium particle propagate along the direction of the, right, they oscillate along the direction of the propagation, and this can be produced in all types of the material, solid, liquid and gases, but this transverse wave can only be produced in the solid, not in gas and the liquid. All right, copy this. So although we will discuss first the transverse wave or wave in string, you can say, but the some basic properties is common for both the waves. We are going to discuss this, right? Some wave parameters. Wave parameters. Right. First is the amplitude. Amplitude. The A. Right. What is the amplitude? Listen one thing. If you consider the transverse wave first, right, the transverse wave or the wave in stretch string, so the particle move up and down, right. So if you consider, this is the maximum displacement, right, this is called the crust, and this is called the amplitude. Suppose this is the y axis, this is the x axis. When the wave is propagating in this direction like this, so the maximum amplitude, the maximum displacement, sorry, maximum displacement of particle, right, of particle from mean position, from mean position is called the amplitude, right. This is represented by A, and this is called the maximum displacement, right. This is also the amplitude from this mean position, right. This is the amplitude. What is the crust? Right, maximum positive displacement, maximum positive displacement from mean position, from mean position, right. What does it mean? This is the mean position. If you consider this the positive direction, so this is called the crust, right. This is called the crust. And what is the trough? Please tell. The maximum negative displacement, maximum negative displacement, right, from mean position, that is, this is the crust, right. If you consider this is the x-axis, so these points are crust, right. This is the thing. Fourth is the time period. Yes, what is the time period, capital T? The time period is nothing but, if you consider the any particle present on the string, it oscillates up and down, actually it performs the simple harmonic motion, right. So it complete the one time taken by it to complete one oscillation is called the time period. It is moving up down, time complete, time to complete one oscillation, right, is called time period, is called time period. Is it clear? The fifth definition, the frequency. Frequency, F. What is the frequency? It is called capital T, number of oscillation made in 1 second, number of oscillation, right, completed in 1 second is called frequency, right. And the frequency is nothing but 1 upon time period, right. The unit of time period is second. What is unit? Is second, SI unit. What is the unit of the frequency? Is per second, right. And which is also called the hertz, right. The frequency unit is called the hertz, and simply it is represented by hertz, right. Copy this.
Sir, in the diagram, the negative displacement points are troughs, right?
Yes, you may. This is crust and this is the trough, right. Please make it correct. This is the trough, all right. Copy this now. So the next point is the wavelength. What is wavelength? Represented by lambda. I think you understand this. Suppose this is the string, right. This is the long string, you can assume, and you are producing the wave pulse, right. Wave pulse up and down. When you move it up and down, the wave pulse is produced, you understand. Then again move up and down, then one, and this wave pulse is is start moving with speed v. This speed of the wave depends upon what? And the property of the medium, it move forward, then it move forward and you move it again, your hand up and down, right? So again one wave pulse, these two wave pulse will move forward, like, is it clear or not? Even up down up down. But instead of this, you made your hand up, down, down, and then up. So a complete wave, if you further, this wave is move further and your hand is move up down, then a complete wave pulse is produced. Are you getting or not? So therefore, if you are moving your hand up, down, down, up, right, like this, you are continuously oscillating, and this may be done by the vibrator. Suppose there is a vibrator which is moving up and down, right? There is a string and there's a vibrator. Suppose there's the electronic vibrator, it is moving up and down. So what will happen? As it is moving up, down, up, down, up, down. So wave is produced. You understand or not? You tell. Further, if you consider this wave is transferred, this wave is moving forward direction, and the complete wave pulse are being produced by this oscillator. Suppose this is the oscillator. You understand or not? Getting? So listen one thing, although we define the wavelength by this is the two crust and these are the two trough, right? These are the crust and trough. So the distance between two consecutive crust or the consecutive trough is called the wavelength, right? This is the definition. The distance between either two consecutive crust, right, crust or trough is called wavelength. Is it clear or not? You tell. Lambda, right? Listen one more thing. If you consider the wavelength, you tell me, if what is the time to produce the one complete cycle is the time period. Listen, up, down, down, and up. So this complete one wave is produced, and what will you say? How much time it will take? Tell me, how much time it will take to move from here or from here to here? So one time period. So time is what? Capital T for one wave. Is it clear or not? One wave in which it move forward with speed v. What is v? V is the speed of wave, and in one time period, what is the distance traveled by the wave? Distance is nothing but lambda, distance travel by wave, right, in one time period. Is it clear? So you can apply S is equal to ut, mean distance is equal to speed into time. What is the distance covered in one time period? Say wavelength, by which it is covering this distance, the speed of the wave. How much time is it taking? V. So V is equal to lambda upon T, and 1 upon T is nothing but F. So what the relation we have? V is equal to F into lambda. What is V is equal to F lambda? The V is equal to, I'm writing this side, V is equal to F lambda. This is the speed of wave. The frequency, right? And what is lambda? It is called the wavelength. This is the relation. V is equal to F lambda. You will remember, and the numerical can be solved. But here you have to remember, this V is nothing but speed of the wave, and the speed of the wave depends upon the property of the material or the medium, and which properties are elasticity, and inertia, right? The speed of the wave depends upon the medium properties, two medium properties, elasticity and inertia, you will remember, right? Also the V is equal to F lambda, you will remember this formula, right? Copy this. So read this question. In this question, a sinusoidal wave traveling along a rope. Suppose this is the rope, right? A sinusoidal mean the shape of the wave is sinusoidal like this, right? This is the sinusoidal wave, you can say, right? It is moving, and it is connected to the oscillator. Oscillator mean it is the device which is oscillating up and down. It generate wave complete 40 vibration. 40 times it vibrate in 30 seconds. Are you getting or not? So can you tell me what is the frequency or the time period? Say 40 vibration in 30 seconds. So one vibration, tell me, 30 upon 40 seconds. So is it time period or not, you tell? So the frequency is what? 4 by 3 hertz. Please tell. You understand this thing or not? Please tell. 40 vibration in 30 seconds. So one vibration in this second. So this is the time period. Frequency is reciprocal of time period, right? 1 by t, say we can find. Also, given a maximum travel along the rope, when you are oscillating this vibrator, the wave is produced, it is moving towards right or left. How much distance is covered? This distance covered by the wave, 425 centimeters suppose. And what is the time? In 10 seconds. In 10 seconds, S is equal to ut. What is the distance covered? Say 4.25 meter. It is given in centimeter. Suppose the speed of the wave assumed to be v. And what is the time it is taking? 10 seconds. So what is the speed? Say 0.4, right? Speed is nothing but 4.25 divided by 10. 0.425 meter per second is the speed. Is it clear or not, you tell? Right? Or you can say the 42.5 centimeter per second. So how to find the, tell me, the wavelength? How to find this wavelength? This is the wavelength. Please tell. We have the relation V is equal to, say, F into lambda. So lambda is nothing but speed, the speed of the wave, frequency of the oscillator. The speed is 42 upon 5. The frequency is 4 upon 3. Right, 42.5 into 3 upon 4. So we can solve, and the answer will be in centimeter. 4 ekam 4, right? Sorry, 4 ekam 4, 0, 24, right, into 3, right, 8, 3. Approximately 31.8 centimeter is the wavelength. All right, copy this. So next and important point or the parameter of the wave is phase, right? Almost student and teachers are very confused with this phase. Although in SHM we have discussed this, the same thing we will discuss here also. Listen one thing, the wave, after some time you will see in the next 1-2 lecture that wave is not a very tough topic if you understand the SHM, right? This is the SHM only, right? I will teach you. What is the phase now? Suppose this is the oscillator and it is connected with the string. This is the oscillator. The oscillator move up and down. Please tell. It move up, down, up, down, up, down. When, or you may form the oscillator by your hand only. If there is a string, when you move up and down, the wave will be produced. I think you have done many times, right? If you take a wave, if you take a string, stretch this and oscillate your hand, so your hand become what? Oscillator. Suppose this is the oscillator, it will move up, then come down, right? Come down, and then move up. So the amplitude is what? Say A, its amplitude. So its corresponding particle on the circle if you make, all right, its corresponding particle, when it start from here, please tell. Right, its velocity is v. This oscillator is performing simple harmonic motion between minus a to plus a. Right, so if it is moving, its velocity is maximum. Here velocity of this point is what? 0. So when it is moving like this, so its corresponding particle is moving in the circle, right, like this. Is it clear or not? When it is coming back like this, so its corresponding particle coming on the circle. Is it clear or not, you tell? So when it move up and down, so this corresponding particle perform this. So can you tell me from here to here, at this point, what is the phase? Please tell. At this point, what is the phase of this oscillator? Pi by 2. When it come back further, pi by 2 is completed. So, and now it is moving continuously down. So the corresponding particle is reach at this point. Is it clear or not, you tell? And then it is further moving towards its mean position. So in complete one circle, when oscillate, move up, down, down, up, the corresponding particle on the circle complete one oscillation. Are you getting or not? So in that way, when you are moving up and down, the wave is complete, one wave is produced. You understand or not? The one wave is produced. All right. Are you getting or not? Please tell. So if you consider this is the point and this is the point, right? When you move it once again, once complete circle, this wave is shifted to the one wavelength like this, and the one more wave is produced. Is it clear or not, you tell? Right, this is the oscillator, it is moving continuously and it is moving with the speed v. The wave is moving speed v, which depends upon the elasticity and inertia. Is it clear or not, you tell? Listen, when this particle is moving, listen one thing, initially this particle is moving, now this particle is moving up, start moving up, right? So what is the phase difference between these two particles? Can you tell? 2 pi. Very good. So between this particle and this particle, what is the phase difference? Say 2 pi. This particle has already gone through the 2 pi and it start just moving in this case. In the same way, what is the phase difference between this particle and this particle? This particle, and it just start its motion. 4 pi, right? So all the particles, right, it has the this particle has travel, right, 4 pi, it is 2 pi, and this is 0. Are you getting or not? Right? Are you getting or not? So in the same way, if you consider the any two particles on the crust, right, this is the crust, this is the crust, the phase difference between the two particles is what? Say 2 pi. In the same way, the phase difference between the two particles consecutive crust is nothing but 2 pi. Is it clear or not, you tell? Right. So phase, what is the phase? It defines, definition I am writing, it defines the position, it defines the position, velocity, position and velocity, position and velocity of a particle oscillating under the influence of the wave, under the influence of the wave, right, under the influence of the wave. It defines the wave. You tell, listen one thing, what is the distance between the 2 points, between this point and this point, or C and C, tough and tough, what is the distance? Can you tell me? is equal to wavelength. Are you getting or not? If the phase difference between the two particle, if this is it has the 2 pi covered, it is 0 covered, right? What is the difference? Say 1 wavelength. Are you getting? So the phase difference between these two particles is nothing but 2 pi. Are you getting? If you consider the any 2 points, consider, suppose this is the wave, right? This is the wave traveling. If you consider this point and this point, or any other 2 points, the distance between them is delta x. So what is the phase difference between the point 1 and point 2? You tell, right? How to find? Look, for one wavelength, what is the phase difference between the 2 points oscillating on the wire 2 pi? For 1 meter, what is the phase difference? Say 2 pi by lambda. For delta x meter, if the distance between the two particles is delta x, so what is the phase difference between these two particles? 2 pi by lambda into delta x. So this is the phase difference, 2 pi by lambda into delta x. So this is the relation between, what is it? Relation, I'm writing the heading over here, relation between, right, phase difference delta phi and distance between the two particles, and the path difference sometime it is called, right? Phase difference and path difference, distance delta x, sometime it is called the path difference also, right? In the wave optics it is called the path difference. Do you understand this relation? Tell me. For example, if delta x between these two particles, what is the distance? Say lambda. Delta phi will be 2 pi by lambda into lambda. Please tell. Right? If delta x is equal to what? Say lambda by 2. What does it mean, lambda by 2? For example, if you consider these two particles, what is the delta x? Lambda by 2 over here. So what is the phase difference? Say 2 pi is equal to lambda, 2 pi by lambda into lambda by 2 is equal to what? Pi. So what is the phase difference between this particle and this particle? Although it is moving towards downward direction, it is start moving upward direction. I will explain. So 0, pi and 2 pi. Do you understand this relation? Please tell. Copy this. So read this question. In this question, the progressive wave of the frequency 500 hertz is traveling with the velocity 360 meter per second, right? How far apart? 2 points 60 degree out of phase. That is the 60 degree, it is pi by 3. The phase difference is given. When the wave travels like this, right, there is always be the phase difference between the two particles. So they are asking the distance between the two particles which are out of phase. Delta phi is pi by 3. So how to find the distance between them? Right, delta x we have to find. This is the point 1, this is the point 2, right? So delta phi is what? Say 2 pi by lambda into delta x. Delta x we have to find. The phase difference is pi by 3, 2 pi by lambda into delta x. So what is the delta x? Is equal to pi will cancel out. This is lambda by 6, right? So how to find the lambda? For this, lambda is the wavelength, v is equal to f lambda. Lambda is what? V upon f. The speed is given as 360 meter per second. The frequency is 500, right? 18 upon 25 meter is the wavelength. So you can put over here 1 by 6 into value of lambda, 18 upon 25. It is 3. 3 upon 25 meter, or 3 upon 25 into 100. It is 12 centimeter. So the distance between the two particles which are out of phase, what is the distance? Say 12 centimeter, right? Copy this. So one more expression we would like to find here. This is the relation between the phase difference and the path difference. But if you consider this is the string and the vibrator is oscillating, right? So when vibrator is oscillating up and down, down and like this, right? If you consider the same point, right? So when it completes the one time period, in one time period, what is the phase is covered? Say 2 pi. Is it clear or not? So therefore in 1 second, what is the phase is covered? Say 2 pi by t, right? So therefore in delta t time, if you consider after delta time t, what is the phase difference into delta t? So delta phi is equal to 2 pi by t into delta t. So this is the relation, right? You may write the relationship relationship between relationship between uh, uh, path phase difference, right, and time difference and time difference. Is it clear or not? Delta t. So this is also the another relation. Delta phi is equal to 2 pi by t into delta t, right? This is the important relation. This is also the important relation, right? You can copy now.